So we are in the physical chemistry class. We need to describe and explain, interpret properties of materials, molecules through some, and understand basic processes through equations, right? It is what physical chemistry does. And the main feature that we take care of is the fact that electrons are possessing quantum properties that are distributed like waves. So in the first chapter, we together collaboratively went over the principles, postulates that now you can forget. Probably there will be some imprints in your memories. And last time we did covered the way how to solve time-dependent Schrödinger equation using solutions of time independent as building blocks, right? So it sounds familiar. Now it is time to approach real world, or at least something that looks like real world. So the slides are ugly, and I do not know why should I show them. I can squeeze everything in 1 minute. So basically, what we are going on. Basically, what we are going to do today is I will make a motivation talk. We are not going to solve many things for next couple of meetings. We are going to apply our skills, and you do have very strong skills and understanding of the whole machinery of quantum theory. We will improve it with time, but you already have the core knowledge. But by now it is abstract. Now we need to make it more practical. And we are going to look not on our universe, but on the other universe. And it is not a universe at a far galaxy. It will be a universe in our abstract imagination. So it will be universe where there are no nuclei. Universe where there are no molecules, of course. There are no atoms. There is only one electron in the whole universe. But we are going to solve Schrödinger equation for such solve everything in this abstract universe, like how this electron will behave there. And just to make our life simpler, we probably may, it is not necessary, but it will help us mathematically. We will shrink, make this universe not three-dimensional, but one-dimensional. So one universe with one dimension and only one electron. It is something that we have enough knowledge to solve it with absolute rigor, mathematically. So what is, I can look and be in the camera. If you set it up as a TV series, then we all should be on the stage. So I still do not understand how I can mumble it for the whole hour, but in very brief, we know how to predict future. We know how to take wave function of any object, including electron in this auxiliary universe, and generate wave function from the past to the future, right? So we are going to do a couple of intellectual steps. First, what would be a realistic choice of the initial condition of the wave function in the past? And here we do not have any mathematical prescriptions. We just need to be to have imagination and creativity and just act as scientists, like designing an experiment in the wet lab. So, and we'll discuss it. And then, well, I'm not passionate. We will design a mathematical formula to describe that electron was prepared to be not everywhere, but localized in vicinity of some point. And then the question what will happen to this electron if we prepare it localized in the vicinity of some point? Can we attribute any of our common sense knowledge to predict what is going on? And after we set up these expectations scientifically, logically, we can try to prove them right or wrong with math. Make sense? So this is the plan. And if you understand this idea, you're basically done with today's lecture. I have some leftover slides from previous years, but you will not get anything in addition to what I already told. So we are starting second chapter. So electron in free space. And I don't want to be ambitious in this writing, but it is like other universe. So I think you're about to finish this one. And I hate homeworks, and I think you are with me, but we need to do a few of them more. So here is another one. And let's try to do it by Monday. If it's not possible, we'll extend, but doing of this homework will be really, and I'll check and repeat on Friday if you still need it by Monday, but it will be really great. Completing this second homework will be very much helpful and auxiliary in our main task that we are doing right now in describing the lone electron in the empty universe. And the questions will be look in the Wikipedia if you didn't have in previous classes. Wow. I think on the image, everything reads from right to left. See, there's a mirror image. It's not possible to use. Very interesting. So the question is to perform so-called Fourier transform of this function. Question is to perform so-called Fourier transform of this function. Did you hear about Fourier transform before? You'll find it in Wikipedia. It's your mathematical muscles are already strong enough, and I know from the previous meetings that at least one attendee of the class, August, did mention or bragged that he's aware of it. So basically, okay, now I see where time goes by. Instead of going to main material, I was explaining what is the homework. Now I can fit 50 minutes. So last lecture, we together were operating quite advanced and fancy terminology. Specifically, we were speaking about expanding wave function in the basis of eigenstates of time-independent Schrödinger equation, right? So here is the little math that if you hear it for the first time, it can be overloading, but it's one of the standard and simplest things, so that a vector can be decomposed as projections on a basis. So this doesn't surprise you. Okay. Now, if the vector is in the space of million dimensions, it can be decomposed on the basis of million basis vectors or infinite dimensions. So functions are like basis states in multi-dimensional space. Right? So any general function can be represented as superposition of some simple basis functions. And the selection, what is our basis, is there is a lot of freedom. So if you are solving Schrödinger equation, we need time dependent. We need to take time independent solutions as basis. But generally in math, there is a in engineering. And I think Kennedy is a major in engineering, right? Say no if I'm going to, if it is wrong, but if it is okay, just you can stay muted. So, and in electrical engineering, when we design or use any processing of acoustic waves, like music or transferring signals for cell phones or digitizing high quality music, the representation of acoustic waves as intensity of these compressions and sparse areas in the air would take a lot of information. Instead, one decomposes sound on contributions from different frequencies. Make sense? So decomposing sound on contributions from different frequencies is what is done to use small bandwidth to pass on a lot of information about sound. And if you deal with, I don't, but if some of you like music so much that you use advanced stereo systems with equalizers, one can mute like bass and increase high frequency sounds. So one can manipulate this distribution over frequencies. So it is what one is doing in electrical engineering. In math, one can decompose any arbitrary function over the trigonometric functions of different frequencies. So one places sets up argument. Here is independent variable, and here is the integer number. This integer number raises on. So this procedure is quite similar to what we discussed. So try, and if you find the solution online, legal activity in today's world. But so basically, one needs to find values of coefficients a and b. By plugging which in this equation, one will reconstruct the function that goes up and down, right? So in the very rough approximation, it will be one cosine, up, down. But if one adds together more and more, it will be higher quality. And I will probably chat more about it on Friday, because no one does homework ahead of time. Everyone does it in the last hour before it is due. Okay. So last time we did stopped at 3 ways to create future, and our favorite way to go from past to the future is decomposing arbitrary function onto basis states, and then plugging in expansion coefficients into this generic stuff with basis functions, phase accumulation factors, and these factors, right? Do you see connection with the next homework? So if our basis functions would be sines and cosines, it will be basically this is answer. This is how to find it, how to find expansion coefficients. Just take wave function. You don't speak the word wave there, but initial function multiplied by one basis functions from the sequence, take integral, and report the answer. And you know that if the original function is periodic and basis function is periodic, then you do not need to integrate over from minus infinity to plus infinity. You just integrate over one period. So I think it is enough hints for next homework. Okay. So what? Because of the virus, I didn't distribute money hand to hand. Otherwise, I would do it. So, what are the currency in the European Union right now?
Euros.
Euros. When did they start to use euros? Like 10, 20 years ago, but before it was national currency in each little country, right? So, which faces are shown on the American national currency?
Presidents.
Guess whose names were shown on the. Guess whose names were shown on the currency in Germany.
Scientists.
At least on one note, it was mathematician, right? So, do you see the name here for this mathematician?
Carl Friedman.
Gauss.
Yeah.
And I think you're aware with the Gaussian function because it is what is used for normalized distribution of grades in the freshman course, right? So how does it look like? Can you show? Yes. So it is also shown here, and there is an equation for it. Any objections? So if our exponential is not imaginary but real, and we put quadratic function centered at some point and put minus up front. So when this quadratic stuff goes up, the exponential decreases. And this quadratic function goes up to the left and the right of the central point, right? So the argument goes up to the both sides of the central point. Therefore, exponential decreases to both sides of the left and right. Yeah. So blank screen is the best. So we assume empty universe and place only one electron there. Electron will obey Schrödinger equation. And it is just kind of natural human wish to start with something that we can touch or imagine. So let's assume that, and we know that it probably will be too hard to push electron to stay in a really, really small area. If you look microscopically, because of its wave nature, it wants to take some space. So we are taking compromise between having it localized for us humans and its wavy nature, which probably drives it to be everywhere. So let's assume that we can prepare electron sitting in the vicinity of a point. If you make a connection to a real world, which experiment can correspond to? Maybe an electron coming out of the electron gun, right? So we in this vacuum tube. So we accelerate it, we give it some velocity, and then it goes with its wavy nature, but it has some space where it is localized. So why don't we take help? Why don't we take help from the Carl Friedrich Gauss and assume that at time 0, electron is taking the wave function that agrees with Gaussian profile, right? So you can protest and suggest something different, like suggest Lorentzian function or do something. And I'm not insisting. It's just one of the opportunities. And now, if we do it, let's make a guess what will happen to this electron as time goes by. So what does happen to the classical particle if you do have initial position and initial velocity? Yeah, so what will be the position at time t if at time 0 it was x0? Imagine that I invite Zane to go and write it here. You can speak it up, but next through the course, I probably will invite you guys to help me with it, if you don't mind. It will be more vivid. So, but now let's relax. So, what would be position of this material point at time t, if you know velocity and we know initial coordinate?
Just do velocity of it.
Hmm?
Times velocity.
Times velocity. Time t times v. It is what you want to say. If you put t equals 0, then the initial position will be 0. But it is not 0, it is x0. How can we fix it?
0.
No, just x0. Make sense?
Yeah.
So if our object of interest is just a classical particle, it moves forward with constant velocity. And if it is classical particle, it doesn't change its shape. Now, if we are looking on the electron that is distributed in space and maybe takes some area, and it also in average has some velocity, what would happen after time period t? So we may guess, we may assume that probably the center will move according to the same law, right? But what would happen to the shape? So now we can make, here is the little piece of true science. Now we are not bound by any limits or equations. Can you just guess? I'm inviting you to guess what will happen to the shape.
We stretch out. Increase in size.
Hmm?
Increase in size.
Super. Yes, you're correct. You do not need math and solve an equation. Yes, increase in size. Hypothetically, it can shrink, it can not change or expand. Or the force opportunity, it could oscillate. But your hypothesis that if you increase in size, it is what we expect to happen. So the area 0 and area at time t. So area at time t will be bigger. So it just take more and more space. So now we do have an example. You do an example of healthy, true scientific developments, how it works. So we together collectively discuss, pose a problem, and then guess a hypothetical answer. Now we stop creativity and start hard work. We need to prove this hypothesis right or wrong. So through hard effort of math, we should prove that it indeed moves forward with constant velocity, and we need to prove that it expands in size. Right? So what would be the way to assess how big it is? I'm going to flip back. So if there is another opportunity that it will change from Gaussian shape to something different. But right now, through discussion, we did agree implicitly that we will keep the Gaussian shape. It's also not explicit. We also need to prove it. But so we made three hypotheses. It will keep Gaussian shape, center will move linearly, and the size will increase. So for center moving linearly, it means just we add here x naught plus dt. And size increasing. What should we change in this equation to make the function to increase size? Which parameter in this equation is responsible for the distance between these edges? Let's check. Check with Tim, Connor, August, Spencer, and Kennedy. So if you are watching, would you suggest what should happen, what should be changed in the Gaussian profile to cover larger width? Please consider either to type or speak into the microphone. If you're speaking, I don't hear it. Maybe if you want, you can type. I think today everyone is unsure what to answer. So you guys were discussing.
Is it x minus? Not the negative x, but the x minus up top? Wouldn't that be the distance between the 2 points, x minus x?
It is a, okay, it is a good attempt. Let me bring a little suggestion. If we practically draw Gaussian function and with different values of sigma, once we put it 1, another time we put it 10. So if you put here a really big number,
So very small.
so then the dividing numerator by small number will be extremely huge, right? So if this sigma is big, then it will be very narrow, right? If sigma is sigma goes to infinity, if sigma is increasing, so we divide numerator by a very large number, so the power of exponential will be very small, close to 1. So if sigma is 0, the exponential will be very, very shallow. Sigma goes to 0. So let me repeat the question. What should happen? What should happen to the function, if to the wave function, to describe the increase in size?
Sigma would have to decrease.
Yes. So now it is another example how we do true science. You guys formulated a hypothetical answer, and now you did convert this hypothetical answer to the math language, to the very rigorous form. So we, by solving Schrödinger equation, we need to extract sigma. Well, first we need to prove that it will be Gaussian all the time, but then we need to extract sigma and find how sigma changes over time. So if it will increase, then shape will increase. If it will decrease, then the shape will shrink. So with this, we have formulated what we want to do. Okay. So how to achieve this goal? So our goal is to prove hypothesis that central point moves linearly and width increases. So what should we do in order to go through this path and arrive? So we are going to get the plane wave concept, which we already started through exponential. We already have momentum operator. We do have time-independent Schrödinger equation, which is probably needed if you want to see how things achieve in time. We have eigenvalues of momentum, but now we need eigenvalues of energy. Why? Because if we practice third way of predicting future, we need energies for accumulating phase in the expansion. Eigenfunction of Hamiltonian. We do have eigenfunctions of momentum operator, which we are going to solve time-independent Schrödinger equation for this free space. Then we are going to plug everything in our third way to predict future and just look what happens. Make sense? So it basically agrees with what we were doing before. So why this exponential function e to the power minus imaginary unit over h bar momentum times x, why it is referred to as plane wave? What is plane there? But please try to discuss and just share any associations. What an idiot gave a plane wave name to this linear function? So let's think together. Our true space is not one dimensional, it's three-dimensional. So later on, we may want to expand this concept into three-dimensional world and set up these periodic waves in the three-dimensional space, right? So if we agree that phase will be accumulating according to motion in a certain direction, right? Let's say along x dimension, and along y and z there will be nothing. It will be equal. So it will be like I don't know. I was thinking about lifting a table, but maybe we have something more peaceful. We have a plane, so and along a plane everything is the same, but as we go forward in the x direction, the wave goes up and down, up and down. So it is a front of the wave. So wave front, plane wave is the simplest example of a wave, and we can fabricate plane waves going in x direction, and y direction, and z directions. And now, just for mathematical simplicity, we give up y and z. But it is very common agreement terminology to call this exponential to the power momentum times x with imaginary unit to call it plane wave. You will not be wrong telling it. And it is especially popular in material scientists, in the community of material science. Okay, yeah, I'm doing good and feeling time with this material. So we already discussed that sigma does increase, and you both immediately told it must increase. So you have a good scientific intuition. Here is just a little overview what we did before. So if you are attending previous meetings, you won't see anything new. So momentum is operator. Previous slide is defined as time derivative of space. Okay? And the eigen functions of these operators are plane waves, right? So by applying this operator to such function, we are reproducing this function back. By applying derivative over space to this oscillatory exponential, we get this oscillatory exponential back. So plane wave is an eigen function of momentum operator. If you in a really strong mood to make notes, you can record it. So plane wave is an eigen function of momentum operator. So here I'm going to declare the expected answer. So if you will do everything correctly, if you practice all mathematical exercises, and I give you warning, it is not an easy journey. It will take more than one lecture to arrive to this result. So it is, you need strength and patience to arrive to it. But what we expect, if time goes bigger than 0, we will have the same exponential function, but instead of x naught, it will be x naught minus momentum times t, and in the denominator there will be some constant times time squared. So it will expand in space even quicker than moving forward in time. So it will be really quickly as t squared taking more and more space. If in the real world there are always walls, there is something that repels electron, another electron. If there are no borders, it will just expand as much as it can. But by now, this is only a hypothesis. We need to prove it. Or maybe something will happen this year and we will prove it wrong. Okay. And I have a sense that it is we are approaching close to the end of the meeting. So we do need to practically practice our third way to predict fusion. So what we are going to do in the class is to take the wave function of the past as Gaussian function, eigen value of momentum as plane wave, and then perform integration and find expansion coefficients. So probably they will depend on this value k or on the value of momentum somehow. Too early to speak about it. And then after we get this ck expansion, so it will be function either of number or momentum, we will plug it into this protocol, into this equation. So by multiplying plane, so we plug plane wave here, eigen value of eigen energy of plane wave here, which we also need to find. But I assure you it is the easiest part. And then put the c sub k that we will find through this operation. And then we will get a wave function of our hypothetical electron in the imaginary universe as function of time. So this is the plan. And yes, we're done. I'll probably show up for the lab quickly, but we will do it quicker than usual today because I need to take an exam tomorrow. Okay, I stop screen sharing. Thank you, Kennedy, August, team. and honor for being with us. And oh, there are some comments. August, Sigma, Spencer, maybe Sigma. Yeah, thank you. I didn't look on the chat line, and I'll try to do it better next time. If you want, you can just unmute microphone and speak. So we're done.
Yes, sir. Thank you.
Yep. Thank you.